Yes.
Okay, yeah.
Okay, again, welcome everybody. This is our program. We are now in week 6, or yeah, week 7. Depends on how you look at it, because we have a spring break in between. But in this 6th week, we're going to focus on the neural networks. So that's an exciting area where a lot of things are happening, as you all know. So we're going to talk about it this week and next week. It's all part of data science. That's the name of this course, obviously, right? So we talked about it already in week 1, but maybe you forgot already about it. Okay, how all these things fit together. What is data science? What is machine learning? What is artificial intelligence, and so on. So data science is the big area where data science is really focusing on, okay, how can we detect patterns and correlations between the data. And we looked at it in the first lectures. We looked at classification, regression, clustering, and so on. Artificial intelligence, on the other hand, is a more broad area, partly outside data science, because there we're focusing on intelligence as, let's say, as performed by machine, right? So not only the computer science is part of artificial intelligence, but also psychology and philosophy, for example. And when we're zooming into this field, machine learning is, let's say, a big part of data science, because that's where mainly all of our lectures are about. And if we zoom in then again into machine learning, a special part of machine learning is deep learning, what we call deep learning. And that's really an acronym of saying, okay, we're working with neural networks, right? And if you're working with neural networks, you're performing deep learning, also with the same idea to find useful patterns in your data. Okay? So that's how it all fits together. We also used this picture before, where we have all the different machine learning algorithms here, or most of them actually, here on this picture. And in this course, we started here in the top part. We looked at obviously, let's say, how to visualize the data, how to look at certain statistical information about the data. Morning or afternoon. Morning. And so we looked at regression, we looked at classification, we looked at clustering. So regression and classification, that's supervised learning, right? Where we have labels, right? So we train on the labels, and we hope to find a model which reproduces the labels as much as possible. And we have the unsupervised learning, which is without the labels, just finding, let's say, the different patterns in the data. So we looked at clustering specifically, and we also looked a little bit into PGA dimension reduction, yeah, which is unsupervised. So we call this classical machine learning algorithms. So these algorithms are have a wide usage. They're used very much, but they have some drawbacks, and that's these drawbacks we can, let's say, eliminate mostly by moving over to neural networks, which is another part of machine learning. So these classical algorithms, they have problems, for example, with recognizing objects, classifying pictures, for example, or recognizing speech. How do you classify audio bits? Yeah. How can you make a distinction between, let's say, a bird's noise of, let's say, different bird species? How can you do that? That you can do that better with neural networks instead of the more classical machine learning algorithms. And also, hot topic. Last couple of years, especially, let's say, in the last year, we see a lot of deep learning networks that can actually generate content. And we all know ChatGPT, and we're not looking. And last week, GPT-4 was introduced. So these developments go very quickly. And with GPT-4, and we're going to talk about it later on, how it works. But GPT-4 focuses on multimodal type of solutions where you can not only generate text, but you can also generate pictures. You can do style transfers on pictures and so on and so on. So the generative networks, they have become more and more important also. We've seen many applications. We will see a lot of websites using these types of neural networks. Okay? Good. What are we going to do today, week 6, this week? we are going to focus, okay, what are neural networks? How do they work, right? So what is then deep learning? What is deep? What do you mean? What do we mean with deep, right? We're focusing on the tools that we are going to use in order to build these neural networks. That is Keras and TensorFlow, invented by Google. We're going to look at simple, let's say, neural networks. We call them perceptron networks. And we're going to look at convolutional neural networks. That's for this week, as you can see over here, right? And then for next week, we are going to look at more exotic type of neural networks. Recurrent, long short-term memory. When you have repetitive data, it's easier to remember. We're going to look at autoencoders. In general, talk about generative AI or machine learning. And we're going to talk about these general or generative adversarial networks. That's the basic building block of doing all these ChatGPT functions and so on, and generating pictures. Okay? So let's then start. What is a neural network? Well, you probably know that neural networks come from the idea of how human brains work. Because in our brain we also have neurons, or rather perceptrons, that communicate with each other. We still don't know exactly how it works, but that's, let's say, the starting point of how these neural networks were invented. It started already in the 50s, I think, in the last decade, but we've seen some, we call that the artificial intelligence winter, where nothing really happened, no strong developments, and I think starting in 2010, there were some people that wrote some articles about how to improve these neural networks, to make them better. And since 2010, we've seen a continuous growth of applications, and also we've seen neural networks performing their tasks better and better and better, right? So nowadays, it doesn't really look like a human brain anymore, but there's, let's say, many math fundamentals now included and so on. So diverted a little bit from the idea of emulating a human brain, okay? And not only the fact that there has been some new developments around how to build these networks, how to make them better, how to calculate it, and so on, but also due to increased computer power, it made it easier to build large neural networks and to train them and so on. And thanks to new, let's say, processors like the Apple M2 with a neural engine inside. The neural engine is basically a large graphical memory unit where you have a lot of, let's say, it's optimized for doing, let's say, matrix multiplication type of things more quickly. Like the GPUs can do these things as well. And Google have released their tensor processing units. Maybe you've noticed if you use Colab, you can also switch on the tensor processing units to perform your training, right? So we've seen also an increased computer power in the last 10 years, and it's ever since increasing. Maybe you know the Moore's law, right? For those that know a little bit about electronics. It used to start with a number of transistors on the chip, I think. And I think there was one of the engineers at Fairchild, I think, later moved on to Intel, I guess. And then he found out that, okay, every 1.5 to 2 years we see a doubling in the number of transistors on the chip. And nowadays we don't see that anymore so much, but we see it more in terms of computer power, or in terms of memory cost and so on. So it's still going on, right? Okay, so neural networks. Okay, what's the basic idea? Well, the basic idea is that such a network will consist out of neurons. And this is, let's say, how it works within a brain, basically. We have let's say, a nucleus here, sending off signals. From input, sending out signals to other neurons. That's basically the idea. So a neural network is basically a collection of connected neurons. It's a network of neurons. And each neuron can receive signals from other neurons and will send it through again to other neurons again. So how do we then translate that idea of how it works in the brain into how it works in a neural network? Well, here you see typical neuron in the brain. If you translate it, you get this. And basically you have a, let's say, a neuron here, which is, and we call it then a perceptron. So in neural networking, we call that perceptrons, or sometimes it's interchanged also with neuron, but basically it's called a perceptron, where the perceptron performs a summing up function. That means it will get input from other perceptrons or neurons. It will apply a weight. It will, let's say, multiply the signals with a weight, and then it's summed up together. And in the end, we will apply an activation function. Why we do this, I will tell you all about it. But basically, this is the basic structure of one perceptron or neuron in a neural network. Yeah. There's one specific one, and that we call it a bias. So basically, in order to train this, we need to establish a value for the bias value, and we need to establish values for all of these weights from neurons that come from other, let's say, signals coming from other neurons, okay? And then we get an output, and that is then again sent through in this way to other neurons, right? Okay, so if we talk about the basic neural network, what we then mean with it is that we have a multi-layer perceptron network. That's how we call it. It's the most basic form of a neural network. And how does it look like? Well, it is, let's say, built up in layers like this. So here we have an input layer, in this case with 4 neurons, neuron inputs, right? We have 2 hidden layers with more neurons here. And we have, at the end, we have an output layer, right? And all of these neurons between these layers, they are fully connected. So each neuron in the input layer is then connected to all of the neurons in the next layer. And every neuron in this hidden layer is then connected to all of the neurons in the next layer again, and so on and so on. Not all neural networks are fully connected in this way. We'll see that later on, but the most simple one is like this one. So what the basic idea is that you feed a neural network with information, you feed it with your data, and then the neural network will generate an output. For example, you will feed the network with pictures of cats and dogs, right? These pictures will flow into the neural network. The neural network will do its calculations, yeah? Basically, it's a trained neural network has fixed weights and biases here. So once it has been trained, you have fixed weights and biases over here, certain values, how to calculate from one layer to another, and then it will generate an output. For example, telling, okay, this picture was a cat, or this picture was a dog, right? So that's basically how it works. So it's a feed-forward network. Information comes in on the left side, on the input layer, and it will generate the output. It will generate the label or the answer, right?
So how would you determine the amount of layers you need and the amount of...
That's tweaking. That's let's say the amount of layers and the amount of neurons, those are, let's say, your hyperparameters. Those are the things that you need to tweak in order to optimize your model.
Is this like a average size or
Mostly, I will come back to this one, but mostly it's better to have more hidden layers with less depth than to have just a few hidden layers with a large number of neurons each. But that's more, let's say, you need to find that out. It might be different for different models. But these are things to find out and to change. So during your training, you might want to train your network again and change the number of layers or change the number of neurons. That's a matter of optimizing your network.
It's like a more difficult choice of the K and the K value.
Yeah, you can compare it with determining your K value. What you do, you calculate it with one K value. You see what your accuracy is or what it will give you. And then you take another K. Or actually, you can do that, maybe you remember, with the grid search or the random search. You can do that here as well, where the parameters are, for example, the number of hidden layers and the number of neurons in the hidden layers. So you can multiple times try to train your network. So what is deep learning? Deep means that you have more than, let's say, at least one hidden layer or more hidden layers. So the more hidden layers you have, the deeper the network is, and that's what we call deep learning. So deep means, okay, we have a lot of hidden layers in between. The bigger the number of neurons and the number of layers, the deeper the network is, okay? Okay, so if you then look into these layers, what is happening, then every layer more or less try to make an, let's say, some sort of a summary of a representation of what's going on in the layer before it. I have some example that I will show you how you can recognize the numbers on a die. Yeah. So how does the little layer look like, and what are the values in between? Okay. So deep learning can be a good machine learning approach when it's difficult to extract features, and much easier to learn representations, especially when it comes to graphical data. You have a lot of, basically every neuron is a pixel when you talk about graphical data or pictures. Yeah.
Is the training supervised? So is there a label
Yes.
on the? Okay.
Yeah.
But that's still the same.
Yeah. So neural networks always have a certain output that we want to see. So what we do is we input data. It will give you some output, especially in the beginning. Nothing has been trained yet. So we have random values. So you get, rubbish output, right? And this output you compare with the label that it actually should be on your training set. So we can compare the output calculated by the neural network with the label belonging to this data, a cat or a dog picture, for example. We compare it, and based on this comparison, we will change the values over here during training, right? That's what we want to do. And if we are approaching, say, the best possible accuracy, then we stop training and we have those values fixed. And then this network is capable of recognizing cats or dogs pictures to a certain accuracy trained in your network. Yeah? Okay, so what are the most common type of neural networks? Well, the most simple one is this multi-layer perceptron that I just showed you. We also have convolutional neural networks. They are not fully connected, and they have different type of layers, which I'll explain later. These layers are optimized for recognizing certain features in pictures, like horizontal lines that we see or vertical lines that we see, etc. Yeah? We have recurrent neural networks. They are not, let's say, multiple layers after each other sequentially, but they have feedback loops. So the output of a neuron can come back also as an input again. So you have feedback loops, right? And you do that because you want to create a certain memory in the network, especially with, let's say, data which is repetitive, like time-based data or stock data and so on. A special form of this is the long short-term memory, where there's also an inbuilt memory to memorize certain, let's say, patterns in data, like in audio. You have repeating, let's say, values probably somewhere in your data, and that's being memorized in this long short-term memory type of neural networks. So you have different type of neural networks depending on the job that you want to do. And then we have these generative neural networks as well, which next week I'm going to tell you all about. Okay, so let's look at an example. Let's say we want to build a neural network that can actually recognize handwritten digits, like this. Well, there is this famous database. It's called the MNIST database of handwritten images. It's from the Modified National Institute of Standards and Technology. And they have a data set with all this type of data. And these are pictures of 28 by 28 pixels in resolution. And they have 60,000 training images. So we have 60,000 pictures of 28 by 28 pixels with a handwritten digit inside. Okay? It contains also 10,000 test images, and Each pixel value can be between 0 or 255, that's 8 bits, yeah, basically. That means that if you have a black picture or black pixel, it will have the value 0. If the pixel is completely white, then it has the value 255. And if you have a gray value for your pixel, it will be somewhere in between, right? So if you then perform or going to use a convolutional neural networks, which are optimized for pictures, the best convolutional neural networks these days, this is from 1 year ago, can reach an error rate of 0.17% on this example, which is pretty good.
Is that better than humans? Or?
Yeah, I think so. Yeah. I guess, yeah. Okay, how does it work? Well, let's suppose let's look at one of these digits. We have 28 by 28 pixels. And as you can see, every black pixel has a value of 0. And every white interface has a value of 1. So we normalize the data. That means we divide by 255. So 255 will become 1. And that's the reason why we see a 1 over here. Okay? So in gray values like these ones, 0.8, 0.8, and so on, they are somewhere in between. Okay? So in total we have 784 pixels, as you can see over here. And we want to feed that in a neural network. And the output should indicate what kind of digit it is. So how many possible outputs do we have?
10.
Yes. We have 10 possible values. It's over here already. Yes. So if you translate it to a neural network, how would the input layer of such a neural network look like, do you think?
Quite big. I think all pixels. The 784 pixels. Yeah.
Yes. So the neural network will have 784 neurons in its input layer, right? So every pixel is fed into its own neuron. Yeah? How would the output layer look like?
10.
Both is possible. But you can have, the easiest way is to have 10. But you can also have 1, but then it should indicate a value. It's also possible. But it's, in this case, they are mutual exclusive. Because this digit only has, well, we want to have a 3 out of this, indicating a 3. So then, in this case, 10 neurons is easier to calculate. Okay? So, this is a possible neural network that could potentially solve this problem. So we will feed in a digit, right? It will flow through the network, and then one of these 10 neurons will light up. It will give a 1, and the others should be 0. Or it could also be that it will indicate a certain probability. And you should do it in such a way that the sum of probabilities is what? 1. Right. So, in this case, for example, if you have a 2, you want this one to light up, and maybe the output is 0.95, and the rest is a little bit. And then you know, okay, this is probably 95% that this is a 2. Okay? So once you have your network trained, that means we have values for all the weights of all these lines that you see over here. So the weights are fixed, and the biases that I talked about are fixed as well. So once the network is trained, it's all fixed. And the idea is that if I feed in this picture, it will indicate the right digit over here. That's the idea. Okay? Now, the interesting question is, of course, how can we do it in such a way that we train all these weights and biases over here? That will probably take some time, yes?
So what's the role of a bias?
Some situation there is a tendency that maybe not all neurons are firing up. So with a bias you can change it a little bit and have this tendency change that it will indeed fire up. Make it more sensitive or less sensitive. That's basically what you do. Yes, correct. So every neuron has also a bias. So what the neuron does is it will multiply the weights with all the outputs from these neurons. It will sum them together, yeah, and then it will have an activation function. I'll talk about it, and then it will output the value to all of these other neurons that you see over here. That's the idea. So, okay, so every perceptron or neuron, like you see over here, every neuron here takes as input the weighted sum of all activations. So all activations, that means the output of all these neurons, they are multiplied by the weights set for all these connections. Yeah, and that will be summed together, and we add another bias. So every neuron also will have a bias for these tendencies. Okay?
Can the weight also be negative?
Yeah. And then this is if you would do this, right? And you would build a neural network like this, then probably your training would not work. Does anybody has any idea why this is? What kind of a function is this? What type of function is this?
Linear?
Yeah.
Linear. Right. So if you would have a network with only linear functions, you would only be able to detect a linear, let's say, dependencies.
The relation between input and output has to be linear as well.
Right.
Yeah.
So if you want to fix non-linear problems, then this is not going to work, right? So some people thought, okay, we need to fix this. Let's introduce what's called an activation function after this calculation. And these activations, they are to build in some non-linearity into these neural networks, right? There are a few that are being used quite often. We already know the logistic function. It's also called sigmoid function, right? For logistic, we had the logistic regression, right? It's the same function. It looks like this. So with negative values, it is 0. But then around 0, it will go up. And then if it's positive, it will give an output as 1. So it's between 0 and 1, and somewhere here in between, right? You could also have a hyperbolic tangent, for example, as activation function that also introduces nonlinearity. Actually, the most, and obviously people have been experimenting with this, okay, what activation function will give us the best performance, and you also have to think that if every neuron needs this type of calculation, you have a lot of neurons, it will add up to your calculation time a lot if you make it very complex, right? So it needs to be quite simple as well. So in the end, most neural networks, they work with this rectified linear unit function. And that means that everything below 0, like if you have a negative weight, for example, it will output a 0, and everything which is positive outputs the same value. We call that a rectified linear unit function. You could also have softmax. I'm coming back to this one when we look at specific networks. But this one is the most important one, the rectified linear unit as activation function. So to summarize, I don't know why this picture is wrong, but okay. This is actually the function performed by the neuron. So we take the outputs of the layer A, those are the outputs of the neurons in the layer before it. They are multiplied by these weights, right? We add a bias for this specific neuron, and then we apply the rectify linear unit to it. And then it will generate this function as an output, which then again will flow to all of these neurons in the next layer, okay? So this is how it works. So again, going back to this neural network here that we used to recognize handwritten digits, how many parameters do we need to train? Because we need to train this, right? We need to, let's say, decide what kind of weights, what kind of biases that we're going to use. Well, if you calculate, we have 784 inputs, then we have 16 neurons in between, we have another layer with 16, and then in the end we have 10 output neurons, right? So in between the input and the first hidden layer, we have 784 times 16 weights. All these lines here. 784 times 16 weights. Every neuron here also has a bias. So we have 16 biases. Okay? Then in between here, we have 16 times 16 weights. And again, 16 biases for these neurons here. Right? And then here, between the second hidden layer and the output layer, we have 16 times 10 weights, and we have 10 biases. This one. If you add it up, this network will have 13,000 values to train. So somehow we need to train this network. We need to establish the right value for all of these 13,002 values in the end. And if we're ready with training, then we have a model finished. And then we have given these 13,000 values their proper value in order for pictures coming in to predict the right digit. Okay? That's basically how it works. Now you might wonder, okay, how does this training work? Because when we start, the network hasn't seen any examples yet. You can randomly set all of your weights and biases. If you put something in, you will get some rubbish. Yeah, doesn't really give you a good output value. So what we do, one by one, we feed in every picture into this network. It will calculate the output, and then we get some output values over here. And again, for the first picture, that will be rubbish probably. We get a predicted output with this tile here. What we do, because that's supervised learning, right? We are going to compare the predicted output here with the desired, the true output, with the label. And then the difference between those two is what we call the error. And obviously, my error might be very big in the beginning, obviously. Now the idea is, when we know this error, how can we update these weights and biases such that we can reduce this error? That's the game that we're going to play. So every time we are going to feed in new pictures, we are going to adapt these weights and biases. And then we're going to closely monitor this to see how this will evolve, right? So what do you think? Would it be good if we stop until we have an error of 0? What do you think? Would that be good?
It sounds like it takes a long time.
That's one thing. It will take a long time. Yeah, sure. Depends on your problem, but it might actually come to a solution pretty quick, depending on your input, how difficult it is. For example, with the example that we're going to show you with the dice, it might take 10 seconds to train to do this.
Overfitting? No.
Yeah, that's true, obviously, because what happens if we are going to train this down to 0? We are training on the training set, right? So for the training set, that will give you splendid values, 0. But if we're going to put in our validation set with the because these cats and dogs, again, we will split them up, or these handwritten digits, we split them up, 60,000 training images and 10,000 test images. As soon as we run through the test examples, it might give you a very high error value. So what would the best way to be to train then? What would the best way to be to train? When because indeed it's overfitting if we train down to 0. So how are we going to solve this problem? When do we need to stop? Because if we're overfitting, that means that this network will do a splendid job in recognizing the training images, but it might do a very bad job in doing validation or test set images. So where do we need to stop training? What do you think? Maybe you might think of a method that will actually know when to stop. We're coming back to this one. This is an interesting question. Coming back to this one. The idea is that we are going to repeatedly input all of these pictures one by one. And every time we're going to look at its output value, compare it with a label, and then update these weights and biases, right? That's the idea. This process is called backpropagation. And I told you about 2010, and especially in this area, some people have made a lot of progress to make it easier to calculate this, because this is very complex, as you can imagine. How to change these weights and biases in order to get a good output, right? Okay, how is this done? Well, this backpropagation training algorithm. So we're going to feed in pictures one by one, and then we're going to adapt these weights and biases. How does it work? How do we adapt these weights and biases? Well, what we want to do is to find the minimum of a cost function. And a cost function has as input all of the weights and biases. And the idea is that we want to optimize this cost function, bring it down to zero as much as possible. Or we also call it a loss function. So we want to bring the error down to zero as much as possible. Maybe you remember this from linear regression. What is the cost function with linear regression? Let's say we have, you know this. If we have, like for example, we have this. We have cars, and here we are going to plot the cylinder capacity versus maximum speed. And if we do that for all cars, then every car has a certain place, and maybe we get something like this. What is your cost function for linear regression? How do we find an optimum linear solution for predicting, let's say, maximum speed, where we know the capacity of the cylinder? How do we find this line? How do we calculate it? What is your cost function? What are we trying to minimize?
The root mean square error.
Yes, we are trying to minimize these errors. Right? We have these errors here. These are the errors. Because if all dots would lie exactly on one line, we have a perfect solution. My prediction will be 100% true, right? So we're trying to find this line such that we have a lowest possible root mean square error. So we sum up, we quadratize all these values, we sum them up, and we take the square root. And that we want to minimize, make as close as possible to zero. Okay, and then we find the line. Yeah. So that also works in backpropagation. We are trying to optimize this loss or cost function, this one. And how are we going to use that? Well, there's no easy way to calculate it. Like in linear regression, you can do the calculation. Bart have shown that as well, doing these matrix tricks, right? With inversion and transformation and so on. That's more difficult in this case. So we are going to approach it. We are going to seek for a solution which is closer to the minimum. Let's suppose we have a cost function defined like this. Let's suppose this is your cost function. So what we are trying to do is try to find the lowest value as close as possible to zero. Right? How do we do that?
It's a gradient.
With a gradient. Yeah. If we take the derivative of this function at any point, yeah, we get the slope, right? Okay? So when we know the slope, we know two possible ways, well, two possible directions where we could try to, let's say, minimize it further or find the minimum. So if we are here and we take the derivative, we know, okay, we can go up in that direction or we can go down in this. In this case, we want to go down. So by doing this, we take steps in order to reach this minimum over here. And we call this gradient descent. We are performing gradient descent. So how can we tweak this function such that we take a step into the right direction, closer to the minimum? Okay? And then obviously you can decide, okay, how big is my step? What is the size of my step? How quickly do I want to go down? Is it just a small part, or do I want to go over here? Or because there's also a risk if I take the steps too large. Maybe we have this. So we call that the learning rate in machine learning. With neural networks, we call that the learning rate. The learning rate should be large enough, but not too large. So basically the learning rate is how big are the steps that we are going to take towards the minimum. And here you see the different steps over here. And probably the learning rate is a little bit too small. The steps are a little bit too small. I know in which direction to go. I only take a small step in this case. So every time we feed in new pictures, we take a step into the right direction. But we can choose how big step do we want to take. If it's too small, it will take a long time. So we do need to feed in a lot of pictures in order to reach this minimum. It will take too long. The training will take too long. If we take a large step, okay, then we are more closer already from the first step towards the minimum. But there's a risk. If the step is too large, then we might end up, and so for example, if you say, okay, I want to sit here, so my step size is over here, like this, I end up here, and then I divert from the minimum. I go the opposite direction. This is not good. So there's a risk, and you will never find the minimum. So the network keeps on training, it will never find the minimum. So one of your hyperparameters, apart from the number of neurons and apart from the number of layers, is your step size. That's also an important parameter to tune in any training of a neural network. Okay? So what we want to do during the training is we want to monitor this. We want to measure it. We want to see how this develops. Right? Okay.
Can I ask one question to the group?
Sure.
How many axes does, in the case of that example, the hello world, how many axes has that curve which you showed on the last slide? Because here, yeah, the one with 13,000 weights you needed to change, right? So how many axes has this cost function? How many dimensions has the graph? How many things do we need to change? How many do we need to
13,000.
13,000. So how many dimensions do we have in this graph? 13,000. And now you see the difficulty of finding that one lowest spot.
Mm.
So we're talking about some hyperplane.
Yeah.
And somewhere there is a lowest spot.
Because this looks easy, right? To find
This looks easy.
But when you've got 30,000.
Yeah. And even three-dimensional it's also easy because you're down on a mountain. Let's suppose you're halfway a mountain and you want to know, okay, how to reach the lowest point here in this area. Then you go, okay, not the right way, not the right, oh, here I go down. So I take a step down. And then depending on how large step I take, the larger steps I take, the quicker I go to the valley, right?
But in effect, when you are on a mountain, you can look at the whole surface. But here, looking at the whole surface, that means that you need to do a measurement of the whole body. So you're just looking, you only look where you take the step.
And if you have such a large number of dimensions, you might end up with multiple minima.
Yeah. Local minima, global minima.
Right. So we want to minimize that by doing some randomness in our training. And this is how it works.
Okay, sorry for the...
No problem. We have our training set. These 60,000 images. Let's say every training image is one instance over here. So how does it work with the backpropagation? What we first do is we split up the training set in so-called mini batches. You can imagine if we wouldn't do it, then for every instance we had to update the weights and biases. It will take a long time. So what we do, we only update it when we have done a number of these instances and more or less take the average from these ones and then do the update. So basically, you take one instance, yeah, You forward pass it, you feed it into the neural network, and this is randomly picked. That's why it's stochastic. So we randomly pick one mini batch. We take the first picture, the first instance, we feed it into the network. We calculate the error in the end. And then we are going to propagate backward and measure the error contribution to see, okay, what does it need to be? We do not change it yet, but we only record it for the moment. Yeah? We put it in a, let's say, in a database. So, okay, these are the desired changes that we need to do based on this one instance. We're going to take the next one, another instance. We're going to take the third one. And then at the end of the fourth one, in this case, and by the way, I don't know how, but 32 is the number of instances that we normally pick for neural networks. That's some sort of a magic figure. Always take 32. That's a good approach.
Nice round number.
Right, nice round number.
For
Yeah.
In computer science.
Yes, yeah, it is. 5 bits, I think. Yeah.
Yeah.
So at the end of all these instances, then we adjust the means, or we adjust the weights and the biases for this whole mini batch. When we have done this one, then we're going to take randomly the next one, do the same thing, and then we'll pick those ones, and then we have done our whole training set. Would this be enough? What do you think? If we fed in the whole training set through the network. Sorry? Obviously, yeah, you need to validate it. And if you come to the conclusion, I haven't reached a very good accuracy yet, what to do? Because my network still has large errors. What do you need to do?
Do it again.
Sorry? Do it again. If we feed one training instance through the network, we call it an epoch. So feeding one times all of your instances in your training set, so 60,000 images in this MNIST set. If we have fed them through the network in this way, we call it one epoch. Okay? So if we see that the errors are still too large, we're going to do it again. Just repeat it. The same training set, feed it again, because we need more time to find the minimum. We need more time to calculate the right weights and biases, right?
Or the instances then randomly distributed
Again, like this one. So we will then take the second one and do this again, like this. And take a random mini batch, start from there, fill it in, and do the same thing with the second epoch, and do the same thing with many epochs. And again, the question is then, okay, how many epochs do I need to do in order to have a good model and a good accuracy? When do I need to stop? We'll come back to that question. I had a question for you guys, but let's see how that will evolve. This is the summary of how this backpropagation algorithm works. This is a very important concept for neural networks, and again, there has been made a lot of progress in this area. So here you see what I've just explained in the picture, okay? You can read it for yourself. Okay, so I already had a question, eh? Yes?
You also said backpropagate, or that it feeds it propagated backwards. Then it feeds the image again.
No, it doesn't feed anything again, but the backpropagation calculation, what weights and biases does it need to be? So you feed in a picture, yeah, you get your output, you get your difference, your error, and then starting from the last output layer, you will then calculate backwards to every layer what the weights and the biases should be. So you start with the weights and biases from your last output layer.
Mm-hmm.
And then
that's how you know which neuron is off.
Yeah, because that's easier to calculate because you're working backwards to find the right weights again. So it's building because you start with the last calculation basically. So that will be very rough, and then more and more you move to let's say the front of your network, and that will give you more, let's say, detail in your calculation. That's the way, let's say, the optimization works.
So if the one is on, and it should be on, and the two is off and it should be on, then the one, you know that all the weights are too strong,
Yeah.
right?
Yeah.
From the previous layer which were firing. So you can switch that. But if you do that, then you know, again, for the next layer, you know, you can do the same thing. So you go
That's
back.
why you need to work backwards.
Yeah.
So it's not feeding backwards, but it's calculating backwards.
Yeah.
Calculating the weights and biases, what it needs to be.
Because you know from the left it should be this, so then this and this should be.
Should change in order to have that output.
Mm.
So you change it and you calculate, for the same picture, you calculate what is the output. Is the output closer to, does the error decrease when I change that weight? That's what you're going to check. And you do that starting backwards, working your way back to the front. That's basically
It's
how
a little bit similar to troubleshooting also.
Mm.
Like, it doesn't work at the end, hey, did it work a little bit before? No, I need to, oh, it did. Oh,
So then the question is again, how many units do I need per layer? How many layers do I need? Should it be fully connected, which we have here? And again, which I already said, deeper networks are often able to use far fewer units per layer and far fewer parameters for good results. So it's rather look into depth than look into, let's say, large layers, right? However, there's a cost, obviously. The deeper your network is, the harder it will be to optimize. So it's some sort of a balance. And it's something to be tweaked and something to find out.
Is that in the learning part or is it more difficult?
The backpropagation part.
Oh, yeah, but I mean, you see, you say the deeper networks are harder to find the correct parameters?
Yeah.
Okay.
It will be more complex.
Okay. Because there's more to vary also.
Not the number, but there are more, let's say, the biases are, you have more biases, basically.
Okay.
Right? Because the biases are for every neuron.
Yeah.
So, okay, so that needs experimentation. So, okay, this is an important overview of how these simple neural network, let's say the most basic neural network, the multi-layer perceptron, how that one works, because we can use neural networks also for our classical machine learning, supervised machine learning algorithms, specifically classification and regression. Yeah. So when we have classification, we're trying to predict, is this picture a cat or a dog? That's classification. In this case, if we have binary classifications, either, for example, cancer, do I have breast cancer or not? Or does this person have breast cancer or not? You either have a 0 as output or a 1 as output or something in between, which gives you the probability, right? That's binary classification. We only have one output perceptron then, indicating its value. And we use the logistic activation on the neurons for the output. And then we get the 0 to 1 probability, right? Like in logistic regression. And the loss function, that means the cost function. How do we like the mean square error, root mean square error in regression? For classification, we use the log loss. Come back to that one. For multi-label classification, like we did here, we have 10 labels as output. Then we have one output percent per class. We have 10 in this case. We apply a softmax function to it, so-called, on the output layer. I'll show you what it is. And again, as a loss function, we have cross entropy, which is basically the same as log loss. But this is just for one neuron. This is for multiple output neurons. So that's classification. For regression, we also have either one or multiple output neurons, but we do not have any activation because we want to have the number coming out of it. So we do not have activation on the outputs there. Yeah. For a loss function, it's the same as regression. We use mean squared error or mean absolute error, depending a little bit on our problem. And that's the same for multiple output regression. For example, when we want to output coordinates, 2 values, or a time series, say a number of values at the same time, then we're going to use this. So back to this one, the loss function for classification. Yeah, let's put it on here. The log, I start here. The log loss or cross entropy is basically the same. These are the formulas. You don't need to know this by head. You just need to remember that if you plot the log function or the log loss function, let's say you have a true value of 1, and if you then input a 1 in the log function, then your output will be 0. So that is a minimal cost. It's to 0. The further you are not closer to the 1, which is the right answer, that's your label. So the more you divert from the actual label, the higher your error rate will be. And here it will go to infinity, basically. Yeah? And the other way around, the log loss, if 0 is your label, but you're going to predict something like a 1, then you have a very high error function, a very high error there. And your error will decrease the more you come closer to your real output, your label output, which is 0 in that case. Okay? Now on softmax activation, we use this for, again, for when we have multi-label classification, so we have more outputs like 0, 1 to 9 in the digit case. Let's presume you have 3 pictures and we have 3 outputs. Then if those, let's say, if your output layer generates a 4, and a 1 from your output neurons, then this softmax function will translate it to this one. It will translate it to probability, and there's an exponential value to it. It means that higher values will be stronger because it's exponential. So if you have 3 output neurons indicating what it will be, then in this way, then as you can see here, for example, for the horse, let's say you feed in you have 3 outputs. It's either a cat, a dog, or a horse, and one of your neurons is an 8, and the other 2 are generating a 2 and a 4 as output. Then the softmax, if you apply it, will generate this. As you can see, the 8 counts much more than the other ones. Yeah. So the 8 will then have a probability of 0.98%, and the other close to 0, and the other one 2%. That's how the softmax works. It will always mean that the sum of your outputs will be always 1. So it's a probability distribution, basically.
And it forces your choice, basically.
Yeah.
He really says, make a choice.
Yeah.
Yeah.
It will, let's say, stimulate the higher values. It will, let's say, emphasize it much more strong. Okay. So that's how neural networks work, basically, how backpropagation work, how this is being calculated, and what error function you are using to train it to make it better, right? This is the list of the libraries that I've shown in the first lecture, I think. Now we're going to focus on these 2 packages. TensorFlow, it's from Google, and with TensorFlow you can build neural networks very easily. It's comparable with scikit-learn, works in the same way. Obviously you have a lot more parameters to tweak, but basically the steps to prepare your data, to train it, and then to evaluate it with your test set, those steps are the same. Okay? We also are going to use Keras because Keras is something that works on top of TensorFlow. It gives you a high-level API, so it makes things more easier. It's with just a few lines of code you can build your neural network with Keras, which sits on top of TensorFlow. If you want to really dive in and you want to tweak each neuron, for example, then you have to dive down into TensorFlow more specifically. But you can do that. Okay, this is how it all works together. So Keras is, let's say, is your high-level API for building these networks. During training in TensorFlow, you could see that in Colab, you can choose how to train them on which processor capacity that you're going to use, either regular CPU or GPU or TPU, tensor processing unit, depending on, let's say, the type of neural networks. If you're going to run CNN, then the best one is GPU. If you're going to run your generative neural networks, then the TPU is the best choice. And for, let's say, the multi-layer perceptron, this is enough. Google will say, okay, yeah, you're not using GPU, but multi-layer perceptron, so go over to standard CPU. Okay? What you can do, that's the nice thing with the neural networks, you can save your model and use that model, if you've trained it, also to be part of an even larger neural network that you are going to use for training other things. So, because you don't already have a, let's say, a part of your neural network which already has been trained, you can reuse it by building, let's say, output layers or input layers around it for your specific problem.
And the safe model is only the weights and the biases and the structure.
Yeah, that your model in the middle will stay the same, that's fixed, but the rest around it will be trained. But your model in the middle already performs some certain predictions very well. So that you can do with serialization. And nice to know also that you can export your model to run on different platforms, obviously in your cloud environment, especially during training. But as soon as you're ready with your model, you should deploy it. So you have to put it into action in your organization. And then you can use TensorFlow serving for this one, in a special environment where you can continuously run trained models for solving problems. You can also export your trained model onto embedded chips. We call that TensorFlow Lite. Basically, TensorFlow Lite, what it does is it compresses your model into a, let's say, a moderate size model, and then you can run it on, for example, Android environments. You can run it on iOS, so you can run it into apps on your phone. But you can also run it on, for example, Raspberry Pi, and even on what's it called again, from our Italian friends?
Arduino?
Arduino. You can also run it on Arduino. So you can export those once trained. You're not training on these processors, but you're running your model on these boards, and then you can build them in, for example, in a sensor, and then you can hang them in a tree, and the sensor is able to recognize different sounds of birds, for example, on its own.
Is there also, because I remember from that there could still be optimization if you want to go to like really small
processors
and embedded platforms?
Yeah.
Okay. And is that also possible with this one, or do you
Yeah.
need? Okay.
So you can start with training here,
Yeah.
like we're doing, and then exporting this and save the model,
Yeah.
and then exporting it onto your embedded chip.
But can you still optimize it, that it's smaller or stuff like that?
Obviously, these chips are not always optimized for doing a lot of training work. So that's why you
No, I see why you do the training differently.
Yeah.
But I remember with a student which also did some optimization to make the model smaller.
Right. That's already done in TensorFlow Lite. So it's
okay.
already optimized for these processors
Okay.
as much as possible. So they've already done that, basically.
In which phase is ChatGPT actually? Is it still in the training phase? So are we training it, or is it already in deployment?
It's in the deployment phase because it only, thus far, it only has seen data before 2022, so up until 2021. So everything that happened after that is not included in the model. But yeah, it takes a lot of time to train these type of models. So what you possibly want to do is continuously keep on training, and then.
Yeah.
But
they do a little bit because you can give
Sure.
feedback, right?
Yeah.
But,
Yeah. So you can add things to it continuously, but the basic model itself, that's let's say your basic trained network is fixed, and then around it you can do things to optimize it, and then okay, you run a new model, and then you, let's say, deploy it again. Yeah, it's quite complex. So okay, good. If you want to use TensorFlow in Spider, if you want to do so, you should import it, obviously. Most of you guys are probably working with Colab, right? it already has TensorFlow pre-installed, so you can immediately import it. You don't need to install it with pip or anything else. If you import it and you have this command like this one, it will give you the version that it's running. I think we are at 2.11 right now when it comes to TensorFlow. Yeah? Okay, so let's see how it works in TensorFlow. This is a very simple regression problem like this one. We have an x axis, we have an y axis. So x is your input, y is your label. And I showed you this example maybe in week 1. So if we, the -1 will give you a -3 as output, as label. 0 will give you -1, 1 will give you 1. Obviously, there's some sort of relation between input and output over here. What's the relation between x and y? If you then make a function which starts with y is equal to, what would it be?
Think about it.
So y is
Times 2 minus 1.
2 times, again?
Times 2 minus 1.
Yeah, 2 times x, your input, minus 1. Right. So basically we're talking about this one. So all of these points like -1, you have this point over here, so all these points are here basically on this line, okay? So that would be a perfect solution, perfect fit, because they're all on the line. In this case we have some diversions and some errors here. The error would be 0 in the end, right? Okay, let's see how this works in TensorFlow. Well, again, you need to import the right modules for it. So what we're going to do is import it. Typically, we're going to name it TF. We also importing Keras. In this case, we need NumPy as input type. Then, what we need to do is to define the model. What kind of neural network do you want to have? And the multi-layer perceptron is just a simple sequential type of neural network. So we need to specify the number of input units, the number of the input shape. How will your input look like? Is it a picture of 28 by 28, or is it just one digit? In this case, it's just one digit. So that's simple. And we only have one layer, and that layer consists of one unit. So this is your most basic neural network consisting of just one neuron, being your input and your output neuron.
Okay.
Right? And as you remember, I showed you this picture. With one neuron, you actually have a, well, you can have a linear relation like
Because
this.
it's weight and bias.
This is your bias, right? This is your weight. Yeah? Okay. So this is the most simple one. It gives you an idea how to do it. So if you've defined how it will look like, you have to build it. You have to build your network. We call that compile your network. You need to specify, okay, what optimizer do I need to have? So what is your training algorithm? And I told you about the stochastic gradient descent as the most used training algorithm for your backpropagation to calculate the weights and the biases, right? So we're going to optimize with the stochastic gradient descent. That's used for the backpropagation. And what is your loss function? So how are we going to measure how good your network is performing? We use that with the mean squared error, like this. And again, we want to minimize the mean squared error as much as possible, make it close to 0 or 0. So we build our model, need to specify optimizer as well as your loss function, like this one. Okay, now I want to define the input. And this is the input that I just showed you. This is your X array, and this is your output Y array, right? It's corresponding with each other. Okay. Then again, the simple, the same thing that we done in scikit-learn is to fit your model. That means we're going to train the model using this neural network. And what I need to specify for fitting is, okay, what is your input? In this case, it's an X array. What is your output? What are your labels? Y array. And how many training instances do I need to do I want to feed through this one? What was epoch again? Do you guys remember?
The mini batch. Sets.
No? No?
How many times you do the mini batch? Yeah.
No? It's not a mini batch.
No, but you had a mini batch, the whole blah blah blah, and then how many times you did that whole blah blah blah?
The whole blah blah is one training set.
Yeah,
Yes.
yeah.
So it says 500. That means that we're going to feed the network 500 times with the whole training set.
Yeah.
So the whole training set is going. In this case, this is your training set. It's
But
just a few.
the mini batch here is it's
The mini batch is not here. It's there's a default value for it, so we don't need to specify it here.
Okay, but it's so small that
Yeah, what's the
Yeah, there's no. We take a mini batch value of 1, I think, in this case, because
So
it
it
doesn't-
basically means that it's yeah, but
it will backpropagate and calculate for every instance. Every digit is going to adapt, let's say, the value of your bias and weight. There's only one of each
and
here.
for each epoch only the order which he picks
Yeah.
first can be different.
So we take this one, we calculate, we change the weights in the bias. We then take this one,
Yeah.
we calculate the difference, we change the weight in the bias. We take this one, and then we have done all of them.
Yeah.
And then we start
In a
again
random order.
with the next one. That's the next epoch. We take this one, calculate the difference, take this one, etc., etc. We keep repeating the whole training set 500 times. Okay?
Cool.
And then again, when we have our model ready, because this is going to end somewhere after 500 times training, we have our model ready. We have our weights and biases set. Yeah. And if we don't want to predict, we use the model.predict method to put in a value. And if we put in this value into this network, neural network, it will produce an output, a predicted output based on the model. Okay? So what do you guys think? If you put in this into the model, what do we get as output? 19. Yeah? Everybody agree? Not quite. Not quite. But close. How, well, let me first ask the question. We are not getting 19, but something which is very close to 19. How come? Why is this? Let me show it. Let me show it. What we are going to do is go over here. Let's see. Here. I hope you all guys can all see it. Let me enlarge it a little bit. Oh.
I think it's visible.
Is this better?
Oh, yeah, this is better.
This is better, right? Okay. So let's connect here. Let's connect first to the environment. Then again, what we are going to do as soon as we are connected here, and then we'll have to wait, prepare, and then we are connected. Let's import the libraries again. We are need to import this one. This will, yeah. As you can see, I've printed TensorFlow version. We are at 2.11 at the moment. So that's good. So let's perform a simple regression example with just one layer. This is your data. This was the data, right, that we had. And if we plot it in we get a nice one. They're all exactly on one line. So it should be a perfect fit, right? So, okay. So let's design a basic neural network. Here we actually are going to tell Keras that we are creating a network here with only one neuron, one layer, and an input shape of 1 digit, right? Now we have to build it. We do that with the compile method.
And you didn't have an activation function, right? It's no activation function.
Because it's regression, we do not need an activation in this case.
Yeah.
And we do not have any hidden layers. If we would have hidden layers, we would have activation still on those hidden layers, but not on the output. But since this is the output as well, we do not have any activation.
Okay.
So here you have your layer, and there are again 2 parameters to train. Just 2 parameters. It's one weight and one bias in this case.
Sounds good.
Sounds simple, right? So okay, let's train a model. Let's pass the data 500 times, and that's what we are going to do here. And as you now can see, it goes quite quickly. Here you see the number of epochs, and for every epoch, it will actually calculate the loss function. We have specified the loss function, right? Which was in this case mean absolute error, and it will actually calculate it with each step. So if we go up,
Yeah, we see.
then the first one, okay, the first ones here, epoch 255, we still have an error with this size. So we don't really have the exact similar answer yet. Our model is not able to produce the right answer yet. If we keep on training, then you see that this loss is decreasing. See? So, but in the end, we are down to 500. We still, here we are, okay. So here, we still have a tiny loss. Why is this? Why doesn't it converge to a solution or a 0 more quickly?
Because it's like a log function, so it never reaches 0.
Yeah,
Like,
it's not a log function, but what is the
yeah.
method?
I don't know
How do you do the back propagation? With what algorithm do you calculate it?
Gradient descent.
The gradient descent. So we're doing an approaching the minimum every time.
Ah.
So we are doing more or less, we'll calculate how close can we come to this minimum, right? And apparently the step size is not large enough to be almost 0 after 500 epochs.
Or too large. That we're now stepping like this.
Yeah, but that wouldn't be possible in this case, in this simple one, I think. Because
It's always positive. Or that's not loss.
loss is always positive, yes.
Okay.
So it's a mean, it's a absolute.
Yeah.
Yeah. So that means, let's predict the outcome. So I now have a trained model. So again, if we want to predict something, let's put in 10,000 instead of 10. If we put in 10,000, what would the, or minus 10,000, can put in as well. What would the outcome normally, what would it be? It's 2 times x minus 1. So we would have minus 20,000 minus 1. It's minus 199, right? So if we do that,
2001 minus 2001 times 2 minus 1.
oh, minus, right. So that's correct.
Oh, it's still way off.
So here you can see that, and I can change it to 10, of course.
Yeah, or 19, you put in 19, right?
Time.
10, 10. Oh, 10, yeah.
So 10, then you get this, right? So it's close, but not close.
But
So
if we would have done linear regression with standard way, we would have gotten exactly.
yeah, but that's because you can calculate linear regression.
Yeah.
This is a simple example, but if you have a very complex examples, then you cannot calculate it. You have to approach it with
Yeah,
gradient
exactly.
descent. So we're approaching also here the, let's say, the
nice
value.
example. Yeah.
So yeah. So the reason why we don't see the actual value is that because we are approaching it with gradient descent, and it hasn't come to a, let's say, a very tiny error yet. How could we improve this?
Step size.
Step size. Try a larger step size.
And where was it in the code, the step size?
I can show you later. It's not in here yet, but I have another example where we can change it, and then you can see the result.
Now it uses a default setting, something else.
Yeah, it's default setting. So
Nice.
okay, good.
Nice.
Let's quickly move on because there's a lot of ground to cover. I'm afraid. Otherwise, I need to do something next week. So this is how TensorFlow works basically. Now let's do another example with classification of pictures. We again have a MNIST database, and they have 60,000 training images of clothes. 10,000 test images. They're all 28 by 28, and they are clothes in 10 categories. We have shoe, we have t-shirt, we have trouser, etc. We have 10 different types of clothes. Yeah. So again, how would my neural network look like? What's your input layer? Same, eh?
Yeah.
So we have 784 input pixels, and we have 10 output neurons indicating what kind of. Yeah. So, okay, how does it look like? I'm not going to show. I can show you the code, but we don't have time for this. So you import it. It's already on the internet. You can straight put it from, get it from the MNIST data set. What we do here is we split it up in a training and a test set. We divide by 255 because we have pixel values. So we want to have values between 0 and 1. With machine learning, we should always have normalized the data, by the way. And these are the possible classes of outputs, okay? If you want to create more layers, so now we need 4 layers. Let's say we have a sequential model. How to build such a network? We have an input shape of 28 by 28, and we want to flatten it. So 28 by 28 is the pixel size, but then we just want to put, let's say, all pixels in one tensor or one array, basically. So we want to flatten it to 784 inputs. The next layer, hidden layer, has 300 neurons, and every neuron has a rectangular unit as activation. The next layer has 100 neurons, again with activation function. And then the last one, we have then 10 outputs. We have a softmax activation. And I showed you softmax means that it's going to normalize the output values. The sum of all outputs is 1, and all outputs will give a probability of which of these 10 classes is the best one. Okay? Then we're going to actually build this network. In this case, we have sparse categorical cross entropy. I talked about cross entropy. Sparse means that we have binary. We have mutual exclusive outputs because every picture can only, let's say, be one of these 10 classes. That's why we use sparse. Stochastic gradient descent is optimizer again, and we're going to measure the accuracy. And when we have built a model, then we're going to train it. We do that with the fifth method again. Input is your training data and your labels of your training data. We're going to run 40 epochs, for example. It's 40 times the training set through the network. And here is your answer of the question, how are you going to decide when to stop? When do you need to stop? Well, again, I can show you. Suppose that you want to, let's say we have here the number of epochs. So the number of times that we are going to feed the training set through the neural network. Let's suppose that we are measuring at every epoch, we are measuring the loss or the error. So we have your loss over here. So with your first epoch, you have probably a high loss, right, on your training set. So what you probably would see is something like this. Okay? Hopefully your loss will, after a number of epochs, it will go down to 0 or close to 0. Okay? What we're here doing over here is that we are also, at the same time, feeding the network with our validation set. We're not going to train on the validation, we're only going to input it. We're not going to change any values or any weights or biases, right? We're only going to input it through the network to see how it will score the errors on the validation set. Probably you will then see something like this on your, well, should use another color, on your validation set. It will probably show something like this. Right? So what's happening? Why is this? Sorry?
Too many epochs.
Because
Yeah, overfitting.
Yeah.
we're overfitting. Where, let's say, how many epochs do you, how far do you need to go? When do you need to stop training?
Before it goes up again.
Exactly. So here we have a minimum. So here, that's the moment where we want to stop training. Because it might be that our training error is still improving. That's fine. But if we see that on the validation set, it's actually our errors are getting higher again. This means that the network will be too much trained on only the training data. It's becoming better at the training data, but not better at the validation set. So this is the moment where to stop. So if we are going to, this is called a learning curve. So if we are going to run this, we also want to see a learning curve so that we know when to stop training. So again, this is what you're going to see. We're going to see for each epoch, we're going to see the accuracy on the training set, but also the accuracy on the validation set at the same time. So for every epoch, we are going to see how it will develop. And obviously, we want to print it out. This is the way to print it out. And here you see this. And actually, we're seeing only the front here. If we would have continued the number of epochs here, it will probably, this one, validation will go up again. So our training is getting better and better and better, training set performance, but our validation might go up again somewhere here. So this is an indication that we're still good. We might want to continue with more epochs to train further, to make it better. Okay? Okay. Good. Then, yeah, how to optimize a neural network? Well, these are the so-called hyperparameters to tweak. So if we're done a training, we see, okay, we've come here, and we stop. We need to continue, and maybe quicker. Let's say quicker come to a solution by improving the learning rate. We can change the number of neurons, hidden layers, and so on. We can
I think nobody's waiting, so that's good.
Oh, okay. Do you guys have some more time? Because I have actually some more data. Otherwise, we'll stop.
Nobody is waiting.
Okay. Otherwise, we'll stop when people are knocking on the door. Okay.
Until tomorrow morning.
Yeah.
Okay. As I said, you can use this grid search, randomized search, and so on, also to automatically do this and define values for all of these parameters. Put them in and run your grid search. It will take a lot of time, probably, because it needs to calculate all of these different combinations of parameters. But then in the end, you will get probably your
Something
best
to do
results.
in the evening when you go to bed.
Exactly.
Yeah.
Yeah. Okay. So how do we prevent this from happening? Overfitting. Well, the most simple way is to simplify your model, make it easier. And actually, what we do with neural networks, we drop out some neurons. We just take them out. And surprisingly, it will more generalize better. It will perform better. So
It's a little bit with the polynomial, like taking less terms.
that's it.
Right.
That's it. So we can take out some neurons, actually. Early stopping, stop the gradient descent when the validation is accurate, doesn't improve substantially anymore. So this might take a long time also. So just stop here. Right? Data augmentation, we're going to talk about it when we talk about training images. Regularization, the weights to limit that the weights are not going to go up very high, or so we limit the range of the weights and use dropouts. Just forget about some neurons to make it better. Okay, and in the end, when we've done our training, we can evaluate it. We can do our predictions, and we can evaluate. We can see how it will score on the test set. And here we see how we are testing on the test set and how to do it. Right? I have the code in the lecture on the internet, so you can have a look at that one. This is an interesting one. What I've tried to do is to make a neural network that can actually recognize dies, and the input is a 0 or 1 for each of these positions. So for 1, you only have 1, like this one, because the number 5-digit position is a 1 and the rest is 0, right? But for 2, you have 2 possibilities. So you should encode both these as well as this one. And that means either a 7 and a 3 or a 1 and a 9 is 1 and the others are 0. Well, so what we need to do is to input all of these examples into the network and to see what's going on. So if you're interested in to see, okay, what are these weights and what do the neurons do inside the network, run this one and it will output you the input and outputs of the hidden layer. So you can see, okay, how does one neuron contribute to defining the value? Yep, see you, Frank. If you're interested, run it and see for yourself. Okay. Another interesting one is the Playgrounds by TensorFlow. It will also allow you to play around with neurons and so on.
Yeah, I played with this one.
Yeah.
And can you maybe explain a little bit what's happening here? What's the features? How should I read this graph, basically?
The features are x and y values in this case.
So that's two neurons then, or what's the?
I think this is in this case we have a classification example with 2 inputs and 2 outputs.
And then the blue is one class, the blue, and the orange is the label?
These are blue and orange labels.
Yeah.
And this is I think the position of the, it should be, I think.
Because I found it a little bit difficult to understand what I was doing, actually.
Yeah. Well, it is defining the clusters, basically, or the classifications, which one belongs to what. And I think here you have the, for each input, it's either belonging to class orange or class blue, basically. But anyway, you can play around with it and have a look. Okay, do we have time for CNNs? Do you guys have some, or do you need to go? I saw you moving already. Do you need to go or?
No.
Yeah, you have some more time? Okay. Because I might take another 10 minutes maybe to explain what CNN is, because that's a common used type of neural network for recognizing pictures, right? You can do, as you could see, with recognizing handwritten digits, you could use a simple neural network already to do it. It will give you quite an okay accuracy, but not very high, let's say 95% or so, 97, I think. With convolution networks, you are close to 100% accurate, right? Well, how does it work? It has a number of different layers in the neural network. We call them convolutional layers. And we have pooling layers. What I do, I'll explain to you right away. What we need to do when we are classifying pictures, we want to look at certain things that we can recognize, like horizontal lines or vertical lines, borders, and so on. So what we do is we do a convolution, or basically a filter, onto the input pixel values. So for example, we apply, when we want to feed this pixel through the network, we are going to change it by applying a filter. So, and the filter is, what the filter is doing here is actually, it will multiply the filter values with these, let's say, dot, it's a dot product, right? So minus 1 times 0 plus 0 times 64 plus minus 2 times 128. And the output of this one will be your new value. It will actually give you a feature value. How does this work? Hey. Oh, I'm not in presentation mode. I thought so. Here we go. How does this work? Let's say this is your original picture. There's a border here, a vertical border in your picture somewhere. We apply a filter to it and it will give you this output. And it works like this. So you look at a filter, and this time it's a 3x3 filter. You apply it to these input pixels, a dot product again, this multiplying with the first one, etc., etc. If you apply it, you will get this value. Yeah. Then you're going to shift your filter over the picture, then apply the same filter and you get this value. If you repeat it, you already see, okay, I have here some, in this case black ones, in this case 1, it will give you 4. And if you continuously do this, and you move it over, you get these values. So what the filter is doing, it's emphasizing a border, rather.
Edge.
An edge, so it's edge detection. So if you do digit recognition, this filter will detect how many edges, vertical edges you have in your picture, for example. And actually these values are the weights to be trained. So the filter to be used is also being trained. It's kind of a difficult concept, but okay, if you apply this filter to this image, you will get this. It will emphasize your vertical lines in this case. And this one, filter, will emphasize your horizontal lines. And the output, this is called, we call this a feature map. It will indicate a certain feature of your input picture. And what the convolutional layer is doing, it will generate in one layer multiple of these feature maps. And these feature maps are then again the input for the next layer. So it will train its features basically. If you want to play around with these filters, this is a nice, I can quickly show you, this is a nice one where someone has actually had different type of filters, 3x3. Oh, you don't see it here? Yes, excuse me. Here you see it. Here. So here is a sharpen filter, for example. You get this. It will look like this. But you can also have, like, for example, a blur filter like this. And if you apply this to this one, you get this. So this is the way that these filters are being made. And these filter values, they are being trained in the convolutional neural network, basically. So you can play around with this one and see what the effect will be, like outline, for example. Yeah. Okay, so let's go back and go here. Here we are. So this is how it works. So if you have a convolutional layer, it will work like this. It will take your input picture. Most pictures are color. And what you need to do is to divide it into 3 layers, because every color is comprised out of red, green, and blue values. Right? So these pixel values can be expressed in red, green, and blue values for pixels. So your input image is 3D. In this case, you might have a picture of 32 by 32 pixels. And it has a depth of 3. So it has color values for red, green, and blue. That'll be your input. Then you apply a 3D filter on it. Let's say 5 by 5 times 3. It's also 3 values deep, 5 by 5 pixels. And you're going to move over this picture, and every move will generate 1 output pixel value. And in that way, you are going to comprise a so-called feature map, right? So basically, you're walking over this picture, and you will generate every time just 1 pixel value here. And that will generate your feature map. And what you're going to do, you're going to do that with multiple filters in one layer. You can specify the number of feature maps or filters that you're going to have in your convolutional layer. In this case, you might have 10. So you have 10 different feature maps. So you have 10 different filters applied to your picture. And this will be the next input for the next layer. Yeah. And it will have a different size, because here you have an input size of 32 by 32 by 3. And this is 32 by 32 by 10. So you get more, it will be more, the depth will increase, basically.
And you will look at different scales, like small items and bigger items.
Right, right. Well, you can, that's convolution. And with convolution, you can also determine how your step size is. Normally you do it pixel by pixel, but you can also jump by 2 pixels or jump by 3 pixels. We call that stride. That's the step size. You can define that as well. And we have something like padding, because if you do this, you can see, if you do this with 3 by 3, you see that the resulting feature map, you don't, it will become smaller. So you will miss pixels on your borders, because you get this. If you don't want to have any pixel loss, what you do is put zeros around your picture, sorry. So you put zeros around it, then you will get the same size back again. Okay? That's called padding. Okay? Okay, good. Then we have not only convolutional layers. In a convolution layer, we also have pooling layers. Okay? Still following? Yeah? Are you guys okay? I think I'm going to make another 5 minutes and then we're finished, because it's a long story, right? A lot of things to tell. Pooling is subsampling or downsampling, basically. So we're going to summarize, for example, 2 by 2. We're going to summarize these values. We take the max value of these 4 and have that as output. So this input, 4 by 4 pixels, will generate an output of 2 by 2. So in this case, it's 25% smaller than the input. Okay? Okay, so how does it look like if you put in this picture after a convolution layer? If you downsample it to 25%, you will get this, something like this. But you still recognize the different vertical lines in some way. Yeah? Okay. We also have dropout layers. We just forget about some neurons. We just skip them. Forget about them. It works. It works. Okay. Well, again, if you're then looking at a CNN, this is your typical CNN network. So we have your input pictures. We make them 3D, right, with the colors. And then we feed them through convolutional layers. We have pooling layers, so subsampling. And we take turns. And then in the end, we have a regular neural network that will indicate, in this case, classes of pictures. Is it a car? Is it a bicycle? Etc. Etc.
And the last part is trained with standard with backpropagation, I think. But the first part is also with backpropagation.
Yes.
All the way from the back to
so
the
it's
front.
all trained with backpropagation. And what is trained here? These are the weights of the filter, the filter weights. Yeah.
Wow.
Yeah.
That's a long chain.
So this one is interesting because here you can see what's happening in between. I can again quickly look at it. And this is this one. So if we draw a figure here, like this one.
Oh, cool.
And we have here the feature maps, and in the end, my last layer, I have a 3 here, right? Now, let's see what happens if I do a little bit like this. So, okay, what's happening? Not much yet. Okay, it thinks it's a 0 a little bit. Yeah? If I continue, still have a 3. Okay, it doesn't, and if I didn't do this, still a 3. Okay. I thought it will jump over to a 9, right?
But the back is great.
Yeah.
Like this.
Yeah.
We have a 9. Yeah? Okay. So you can play around with it. The link is there. You can see, okay, here you see these features,
This is
the roundings. Yeah? And then this is your output layer with the probabilities in color of what it thinks the output is. Okay? Okay, good. Let's finish off because you guys must be too much information. Obviously, it's an overload, but there's a lot of things to tell, obviously. Here is the example on how to build a neural network for the classification of these fashion pictures of 28 by 28 pixels, right? looks like the same thing again, importing, have your training and test sets ready, like this one, standardize the data. Here is building the model. So here you build your convolutional network. Here you have a convolutional layer, you have a max pooling layer, and you specify the size of the convolution. Like in this first one, you have 64 filters or feature maps, and each filter is 7 by 7 pixels to be trained. And the input is 28 by 28 pixels that you see over here. In this case, we have no colors, so the depth is only 1, so we have gray values. If you have color, this would be 3, okay? And then we see all these layers here drop out, flatten, and in the end we have softmax again for indicating which of these 10 pictures is what. Okay, compile it again, optimize this a new one. Adam is adaptive moment estimation, and that means that the learning rate is being adapted while it's trained, because you can set your learning rate. It will be the same all through the training, but this is adaptive learning rate. Can work as well. And your training with 10 epochs, and we're going to look at the validation results at the same time, right? And then we get something like this. These are the loss functions for both training and validation, and these are the accuracy. So we have a 91% accuracy already in our first training. Yeah. So with 9 epochs. Okay. Around 91%. Remember, with the standard multi-layer perceptron, not a convolutional one, we had 87. So we had already an increase of 4% without any further tweaking yet. Okay. Code is in on TensorFlow. When you're doing training of images, you do data augmentation. Means that for every picture you will generate alternatives, like shifting 1 pixel to the left, shifting 1 pixel to the right, turning a little bit. So you augment your data, you're going to multiply it by 100 times. So you get 100 times as much pictures as you normally would have. Because they're all the same, but they are just changed a little bit.
Can you do this automatically?
Yeah, of course. Shift, rotate, scale, clip, zoom, whatever. Yeah? Okay. This is, and I'll finish with this one. The nice thing with CNNs is that there are many problems that you can actually translate into picture problems. For example, if you have time series, something called a recurrence plot. I'm not going to dive into it how to calculate it, but in fact, this is a recurrence plot of this input. If you have, let's say, regular frequencies in your data, you will see it in your recurrence plot. Also, linear trends are going to be seen, and also time series. So if you want to learn these time series and recognize them, make a recurrence plot, and then use recurrence plots for doing your classification or regression. That's basically what you do. There's an example I have it on also on Canvas, where there's a lot of smartphone sensor data. So what you can do is this sensor data, put it in a recurrence plot, and then the recurrence plot will look different when you walk, when you are standing up, when you're on a chair. You will have different recurrence plots. So basically, you have changed the problem into classifying recurrence plots. Right? Another example is audio signals. And Bart already talked about Fourier transformation. Basically, what it's doing is translating, let's say, a time, let's say, signal overview into a spectrum overview. And what you can do is to change an audio signal also into a what we call short-term Fourier transform picture. What we do, we take snapshots of this data. We're going to translate it into a spectrum. So this is indicating which frequencies are, let's say, into the signal, like in a spectrum. And then we're going to, and we do that only for a short, let's say, sample. And then we put all these frequencies diagrams after each other. You get a picture like this. So you change your audio signal into a picture again. And then it's a matter of classifying pictures in a CNN. Yeah? Right. I have a simple audio recognition example. Yes and no and up and down. And it's recognizing keywords, how to build it, and how to do it with a short-term Fourier transform for those that want to dive into this. Okay, well, here you see the advance of all these CNN architectures. There are a lot of different architectures and combinations of, let's say, dropouts, convolutional layers, and so on. I talked about transfer learning already, that you can export your model and use it in other models as well as part of your own model. You can save your model. This is the way to save your model and reuse it in other environments. And well, I'm going to skip the one, coming back to it later. So far, this introduction on neural networks and CNNs. That's an important one, CNN. What I want you to do is to take the wine data again and predict the quality score, but then using a neural network. So try to build a neural network that can actually try to find the quality of the wine. And do it for good and bad. So every quality 6 and higher is good, and 5 and lower is bad, for example. Play around with the hyperparameters, see what it does, and compare it to the other traditional ML methods. What do you see? How does it compare? The code examples are already on Canvas. So with these code examples, you should be able to do this exercise, I think. So we're going to have a look at it on Thursday. So I'm curious to see if you can build your own neural network and, let's say, use it on the wine data set to predict the quality. Okay? And, well, we're going to further look at your product, if you have the data, which methods do you use, and so on and so on. But first, Thursday, we're going to look at the neural network and their homework.
So that's homework for Thursday?
This is homework for Thursday. It's also on Canvas,
Okay.
so it's over there. So try to build your own neural network, put in the data wine set, and try to predict quality with the neural network.
I think that might be a bit tough for me, because I also have my internship tomorrow, and then we also have ASR experiments
Okay.
this week.
You might want to do it maybe then next week, because we would appreciate that everybody in their report also uses a neural network as one of the methods in your own project, obviously. So you build one anyway, right?
Yeah.
And we're not asking, well, we had some groups that actually built some CNNs for recognizing pictures. There was fixed fish, koi fish pictures. They were somehow standardized. They put them in the CNN and they tried to predict the price level with it. So the labels were the prices of these fishes. And they put in these fishes. It was quite okay.
Specific.
Yeah. So that can be done. But the minimal thing for you guys to do in your own project is to at least use a multi-layer perceptual network, the first one that I showed, let's say fully connected, and then apply it to your data set and see what the results are. Okay?
But is that, so it's for Thursday or Monday?
This is for Thursday.
Thursday. Okay.
For the wine set is for Thursday, but again, you need to do one anyway for your own project.
So, and I think, I don't know if Paul is still in the meeting. He had a question regarding our project.
Right.
I don't know if there's still
So I stop the recording.
Yeah, it's good.